Welcome children. Today we are beginning with a new chapter that is inverse trigonometric functions. If you look at this word inverse, you will be able to relate it to the previous topic which we have done from relations and functions. We saw in that chapter under what conditions it is possible for us to find the inverse of a function. So when we are saying inverse trigonometric function, it means we are trying to define inverse of the trigonometric functions. But first we need to ensure that trigonometric functions are invertible also. If they are not invertible, then we cannot talk about their inverse. And if they are not invertible, can we make them invertible under certain conditions? So that is all we have to check. Now for a function to be invertible, it has to be 1, 1 and onto. You can see I have written all the 6 T ratios we have discussed in our previous classes, the trigonometric functions, what their domain is and what their range is. We'll quickly go through them. Then we'll try to make out in inverse trigonometric functions, in order to make them possible, what particular restrictions should be applied. You are aware that sin x is defined for all the values of x. So its domain is x can take any real value, but corresponding to its range will be always -1 to 1. You can see this is the graph for sin x. As x takes various values as angle, you will find the curve takes its peak at 1 and it is at its lowest value at -1. So it remains between that only. No matter what angle x is, y always comes out to be a number from -1 to 1. Same is the case of cosec. X can be replaced by any real number. It can take any real value. But corresponding to that, cosec comes out to be between -1 and 1. When we come to tan x, we know its domain will not be a set of real numbers, because there is an angle or a set of angles for which tan x is not defined. Every time this angle is odd multiple of pi by 2, we are not able to define it. At 90, any angle which coincides with 90 degree or 270 degree, for that tan x is not defined. So while defining its domain, we eliminate odd multiples of pi by 2 from the set of real numbers. So the domain is r minus odd multiples of pi by 2. But corresponding to that, the value of tan x comes out to be anything from -infinity to infinity. So its range is r. You can see this is the curve for tan x. See, as the angle is increasing, the angle moves from 0 to pi by 2, it becomes difficult for us to define the value of y at pi by 2, because at that angle tan x will take indeterminate form. Same in case of minus pi by 2. Okay, but you can see the highest value of y and the lowest value of y cannot be defined here. So it can be any real number from -infinity to infinity. Same is the case of cot x, its reciprocal. The only thing is cot is not defined at multiples of pi. So that is removed, all those angles are removed from the set of real numbers. When we come to sec x and cosec x, accordingly the angles for which it is not defined, those set of angles are eliminated from the set of real numbers. So this is what we discussed in class 11th. Now for this we will try to define the inverse trigonometric functions. So one by one we will go by them. See, you can easily understand, if sin x is a function from R to this closed interval, that means in order to define its inverse, I need to define a new function from the set closed interval -1 to 1 to the set of real numbers. But we need to see, this way will it be a function or not? Okay, so you come to this graph again and you see, you will find there are infinite angles for which sine assumes same value. If we look at the curve, sin x is not a 1, 1 function. It is a many 1 function. I'll quickly give you an example. At 0 degree, sin x is 0. At pi also it is 0. At 2 pi also it is 0. So every time the angle coincides with pi or it coincides with 0, sin x comes out to be 0 only. So for many values of x, sin x is having same value. So we quickly come to know it is a many 1 function. If it is many 1, it is not bijective. We cannot define its inverse. So we need to put some condition on it so that we can make it invertible. Same happens with each of the trigonometric function. You look at the graph of sin x, you will see, cos x, you will see for various values of x, cos x takes the same value. You look at tan x, look at this stretch of the curve. This is same as this stretch. You can see in both these stretches, the value of x is different, but the value of y may come out to be same. So again a many one function. This is the curve for sec x. This is also a many one function. So if you see, all the trigonometric functions are many one functions. So how to make them one one? After putting some conditions so that we get closer to the required condition, which is the function has to be bijective. So with 1 1, they are not 1 1 functions, so there we have a problem. Let us quickly see whether they will be onto or not. You can see this is range we have defined. So whatever element is here in the interval, every element of domain is having some image here. So none of the elements in these sets are unattended. They all are images. We have written the range here. So obviously it is an onto function. So the only problem lies with the 1 1 part. If I make it a 1 1 function, I will be able to define its inverse. So let us quickly take some of the examples. Look at this part. You will find, look at the function sin x. If I keep on proceeding with this curve, you will find same stretch of values of y can be found in various stretches. Look at this part of the wave. This is exactly the same as this one. Is it or not? If over here, if I say this is angle minus pi by 2, for it sin x will become minus 1. Now I am highlighting a particular portion of the curve. See from here to here. This particular part, if I make it thick, what do we see? When x takes various angles from minus pi by 2 to pi by 2, y will take the values minus 1 to 1. This means what? Within this interval of angles, that is minus pi by 2 to pi by 2, I am able to get every single real number from minus 1 to 1 as an image. So if I restrict my angles to this part only instead of R, that means if I say the range is only from minus pi by 2 to pi by 2, then you look at this particular part. In this part, the value of y is not getting taken by two values of x. From minus pi by 2, each angle is different from other and x is taking different values. And corresponding to that, y is taking different values. So if I restrict the angles, see we are defining the function from here to here now. But here I have to put restriction. So angle cannot take all the real values. We will restrict it to certain intervals. So if I fix it to minus pi by 2 to pi by 2, you will see this function will now become 1 1. And we will be able to define the inverse. Okay. Now you may think why only this stretch of angle? If I go for this particular part, pi by 2 to 3 pi by 2, then also I am getting all the possible values of y, that is from 1 to minus 1, or let us say as the angle is increasing, the values are decreasing. The curve is falling, you can see. So we can go for another interval. Why only minus pi by 2 to pi by 2? It can be pi by 2 to 3 pi by 2 also. We can further go for this stretch of angles also. So you can see we can have various ranges for which this function can be made 1 1. But we will take a particular range which will be termed as principal value branch for uniformity. Not this is one branch, this is another branch, this is another branch. If you see, this is also another branch. So infinite branches we can get, for which y will take the values from minus 1 to 1. So what we need to do is, as x is a number from -1 to 1, I can get all these values for x corresponding to which angles? From -pi/2 pi/2 is one set, but same can be obtained related to the the angles which may be from pi/2 to 3pi/2, or which may be from, say, this is -3pi/2, -3pi/2 to -pi/2. But out of all these branches, one will be termed as principal value branch, which we will be assuming. Now, in the same way, you can see I have put a restriction on the set of real numbers. I have taken a particular interval which is a subset of it, for which this becomes a 1-1 function, and we are able to define its inverse. Now, same holds for rest of the functions also. Look at Cosec. What I will do is, again, see, now if you come to this part here, whatever values x will take, that will define the domain. So x can be any number from -1 to 1. But corresponding to this, which particular range of angles we should take? See here now, when we move from 0 to pi, we get all the values from -1 to 1. See, at pi it is -1 and at 0 it is 1. So this is one range. We can have another range from pi to 2 pi. But as I told you, there can be many ranges. We will be taking only principal value branch. So for uniformity. So for cos inverse x, you can see when x is assuming all these values, the angles corresponding to them can be restricted to the closed interval 0 to pi. So here, for different real values from -1 to 1, the value of cos inverse x is coming out to be a different angle from 0 to pi. Now the same concept we need to apply for each of them. Quickly we will discuss tan inverse x. So tan inverse x, now its domain is R. So these real numbers are getting mapped to which particular angle so that it becomes 1-1. So you look at this curve. As you can see, domain is set of real numbers. That means x can be any real number from -infinity to infinity. So you try to locate the angle on this curve which will provide you these real numbers. Look at this angle -pi/2. At -pi/2 we are not able to define tan x. Okay. So at -pi/2 tan x is taking, we can say the value is not defined. So the real number corresponding to tan -pi/2 can be taken as -infinity. We don't know how small it is. In the same way, corresponding to pi/2, we don't know how large it will be. So the values -pi/2 to pi/2 can be obtained for the angles from -pi/2 to pi/2. But keep in mind here, we are not going to include these two angles. Okay, so the interval has to be open. Neither -pi/2 will be included nor pi/2. Now, same set of real numbers can be obtained corresponding to another range of angles. You can see here, this is the identical curve. So, if I take the angles from pi/2 to 3pi/2, then also I will get all the values from -infinity to infinity. So, as I told you, various branches are there which are going to support it, but one out of them will be termed as the principal value branch, which we will be considering. Now, in the same manner, though I have not drawn the curve for cot inverse x, you will see when the curve for cot inverse x will be plotted, or for cot x will be plotted, you will see all these real values can be obtained corresponding to the angles 0 to pi. Again, it is an open interval. At 0, cot x is defined. No, cot x is not defined at 0. At pi/2, at pi also it is not defined. So, from 0 to pi, you will see it will take values from -infinity to infinity. Now, for sec, I have drawn the curve sec x. We know that cos x is between -1 and +1 because sec x is reciprocal of it. So sec x will be either 1 or greater than that, or it will be, you can see here, sec x is either 1 or greater than that, or it is minus 1 and less than that. Same happens for cosec inverse x also. Look at the curve for sec x. It is 1 or above that, it is minus 1 or below that. So we need to see if these are the values for the domain of sec inverse x, because now we are talking about inverse, so the domain of sec inverse will be this. So for all these values of x, we have to see what will be the range. But see, again, as we have discussed, these are all many one functions, so I cannot take this entire set as the range. A part of it has to be taken as a range so that it becomes a one function. So let us try to locate what that will be. Now coming to this part, you will see, look at this, sec is becoming minus 1 at pi. It becomes 1 at 0. Okay, and the domain contains all the real values except this interval. Fine. So in order to define this, what we can do is, we know that at pi sec is becoming minus 1 and the values under it, below it comes out to be. So let us see what will be the values, the range for it. If I say the interval 0 to pi, okay, if I discuss this, we need to see, are we going to get for these angles every possible real number written here. So we'll quickly see, at 0, sec x will become 1 and at pi it will become minus 1. Now what about the angles in between? So look at the angles between 0 and pi. You will see when we move from 0 to pi by 2, sec x becomes greater than 1. And when we take the angles from pi by 2 to pi, sec x becomes less than minus 1. So which numbers this domain is defining? It is defining the numbers 1 or greater than that, or minus 1 and less than that. So we need to justify that this interval will include all these real numbers. So you can quickly see, I will explain again. At 0, sec is 1, and between 0 to, see, between 0 and pi, there will be an angle pi by 2 also. So from 0 to pi by 2, sec takes the values 1 and above. And from pi by 2 to pi, it takes which values? At pi it is minus 1, and between pi by 2 and pi, we get the values less than minus 1. Okay, but see, from 0 to pi, there is one angle where it is not defined. So that angle needs to be excluded from this interval. Okay, see here, this will not be an open interval because it will be closed, because at 0 the function can be defined, at pi also it can be defined. So for all the angles from 0 to pi, we are getting all these values of x. So if x is taking all these values, then corresponding to that, sec inverse x is going to assume all these angles. But here at one angle it is not defined, so that is what we will exclude. Now again you will see, we can have many such ranges. I'll quickly give you an example. We can even go for the interval minus pi to 0. Okay, you can see from minus pi to minus pi by 2, I am getting values minus 1 and below that. From minus pi to 0, I am getting values 1 and above that. And in that interval at minus pi by 2, it is not defined, so that needs to be eliminated. Again, as I told you, there will be infinite such ranges which can be used here other than these, but we will be mentioning only principal value branches as the required ranges here. Okay. In the same manner, the principal value branch for cosec inverse can be evaluated. You will find cosec inverse x takes, cosec x, if we first discuss, it takes all the values which are 1 or greater or minus 1 and smaller. So you will see cosec inverse x will become minus 1 at minus pi by 2. And it will become plus 1 at pi by 2. Okay. And see, we need values greater than 1 and smaller than minus 1. So if you look at the curve for cosec inverse x, you will find all the values are included. The values which x is taking, they can be covered within this interval of angles. But you will see in this particular interval, there is one angle 0 for which it is not defined.